Okay, so these are the results generated, and we are looking at the .out file. But the best for us to visualize the result is, of course, using the result feature of the CMG. Okay, so let's just close and then go to 3C and then just put the .sr3 onto the results. All right. Okay, so now we are already in the result. Okay, as usual, let's just go down here and then check the IK2D view. If you're interested in the 3D view, you can click on this one. But I prefer IK2D view and then display. Let's check the pressure first. Okay, so the pressure barely increases because we are dealing with, infinite aquifer, and we only inject the CO2 within a period of 1 year. So basically, the reservoir pressure increase will be very insignificant, okay, for the infinite aquifer. And then, as usual, we are interested in the gas saturation. Okay, all right. So you can see the CO2 plume at the top. It extends quite far from the well because we are dealing with infinite aquifer. We can inject more CO2. Okay, so we have more CO2 within the aquifer. So at the top, you know, it propagates farther from the well. And we can also see the yellow zone here. It it is because, the hysteresis trapping, the residual trapping. Okay, and then let's check as usual, this one. Okay, all right. So this is the profile for gas saturation below the critical gas saturation. And you can see the shape is quite interesting, and we will compare it with the case with limited aquifer later on. And we are also interested in mass density because we are dealing with, you know, the solubility trapping. So let's find water mass density or water mole fraction of CO2 starting from 0. Now it becomes interesting, right? We have downfall or downward movement of the, brine saturated CO2. Again, brine saturated CO2. Okay, because now the CO2 can be dissolved into the brine. So we have brine saturated CO2. So of course, within this brine saturated CO2, we have mole fraction of CO2. And why do we have downward movement like this? Why do we have so-called rain drops like this? It's because, let's check the water mass density starting from this value. Again, this because the brine saturated CO2 is more dense than the normal brine. It's heavier than the normal brine. And because it's heavier, it's because it's more dense, it will go down into the bottom of the aquifer due to gravity, right? So we have actually convection within this case, okay? We have, again, convection currents, okay, created in this case because now CO2 becomes soluble. It can be dissolved into the water, okay? The heavier brine will go down, and the normal brine, the lighter brine without CO2 dissolved in it, will go up due to buoyancy, okay? And again, if we have water saturated CO2 or CO2 saturated brine down there, it makes the CO2 sequestration even more secure, okay? Because it is much more difficult for the CO2 to escape, okay? It's quite difficult for the CO2 to escape from the top section of the reservoir because after that we have the cap rock, we have the barrier, and it can be even much more difficult for the CO2 to escape from the bottom section of the aquifer. Because if CO2 want to escape to the upper side, it must experience hysteresis trapping later on. It must experience the residual trapping later on, which will reduce the amount of CO2 that can escape at the top section of the reservoir of the aquifer, right? Okay, so now let's compare the case data source with the infinite or limited aquifer.